is the university that has inside also the observatory.
Okay, okay, it's too much.
Nie będzie rosło.
So good afternoon, everyone. It's my pleasure to welcome here our special guest, Pasquale Panuzzo. Pasquale works in Paris, in the Observatoire de Paris, and he's involved in the Gaia mission. And he's originally from Italy, spent some time in Padova, Trieste, as far as I understand, and he's working for the last 10 years on Gaia data, and he's the leader of the discovery of Gaia black hole 3, from pre-release Gaia astrometry, and that will be the focus of this talk. So, Stella, the floor is yours.
Many thanks. Many thanks also for the invitation of this observatory. It's really an honor to come here and also to visit your beautiful city. I would start to say that I'm a bit embarrassed to give a talk on the black hole while I'm not really an expert in black holes, with so many black holes experts here. So I beg your pardon if I will say something silly. I will try to not. And I would like to start stressing that although I'm the lucky guy that found this black hole in the Gaia astrometry, the merit of the discovery should go really to the Gaia consortium, DPAC, because the results, the discovery is results that come directly from the Gaia pipeline. So yeah, I'm just the lucky guy that found it. I think that most of you know the Gaia mission, but I want to summarize a bit the mission for those that do not know. Gaia is a cornerstone mission. Was approved in the first 2000. And its aim, it is an astrometric mission with the first aim to make the most precise three-dimensional and dynamical chart of our galaxy. Of course, the fact that it is a survey mission means that it doesn't do only this, but it has also studies the stars and also the galaxy outside ours, even object in our solar system. So it's a mission that is having a large impact on the entire astronomy community. It observed the sky in three ways. Via astrometry, but also via photometry and spectroscopy. Let's say we can say that it has three instruments, although they are, I can show you here the payload, the focal plane here with all the instruments that are integrated together. We have 62 CCDs that are dedicated to the astrometry, and this CCDs also measure the G magnitude, which is limited to magnitude 20.5, and the aim of the mission is to get a parallax precision of around 20 microseconds at magnitude around 14. Then there is a photometer that is actually a spectrometer. Indeed, it is composed by these two prisms, which produce a low-resolution spectra from which you get you can do photometry in the band that comes from the UV to the near infrared. And finally, there is the RVS, radial velocity spectrometer, which is a medium resolution spectrometer that observe around the calcium triplet in the near infrared. It is how the name says is specialized for the measure of the radial velocities of stars, and it is limited to magnitude G 17, 16. A few words about the Data Processing and Analysis Consortium. Is the large group of people, around 450 people in Europe, with the participation also of some other non-European countries, which has the heavy duty of processing the Gaia data, validating them, and distributing them, but also analyze them, calibrate, and also look at the health of the satellite. One word about the proprietary time. There is no proprietary time on Gaia data. The DPAC prepares the data for the release, for giving to the community, and the aim is not to do science. We just do some performance validation paper that show the performances and show how good are the Gaia data and how they can be used. Gaia data are released in cycles. There were already 3 data releases, major data release. The last one is DR3, was in June 22, and it was based just on bit less than 3 years of data. The next one, which we are working hardly on this, is DR4, which is expected in the second half of 26, and will be based on around 5.5 years of data. As you know, maybe the entire Gaia mission will cover 10 years of data, and this will be released in the final release, year 5, which is expected in 2030, 32. So
is pre-release data published or unpublished?
There is no pre-release data that is published. Just this one is the only one. There are some focused release, a small release on some focused products There were a few. It was this year, I think, on some topic. Okay, like it was for example, objects in of the solar system with updated orbits. An introduction on stellar black holes. You know this maybe better than me. In our galaxy, the black holes, the stellar black holes that are the remnant of the evolution of massive stars, are most of them were discovered because they are in binaries, like shown here, and they grab some matter from the companion, and the matter that is falling on the black hole creates an accretion disk, which easily becomes bright in the X-ray. But if the black hole doesn't have a companion, or if has a companion that is too far to bring to steal matter, we have a dormant black hole that doesn't emit any light, and this way is extremely hard to detect. There is one black hole that was found unbounded, discovered via microlensing. Some of you work on this black hole. There are 5 candidates found from microlensing in Gaia. A few black holes discovered with radial velocities, well, finally, Gaia is expected to give a good contribution, a great contribution to this field. It is expected to find a large number. We don't know exactly what. Let's say that the estimate today are around 100 black holes, dormant black holes in binaries. How Gaia finds black holes? Well, there are 2 ways. Well, Gaia can spot compact objects in general in several ways. If they are in binary system, the black holes can be found via astrometry, radial velocities, and photometry. You have some example. So you have the motion of the source that doesn't follow a single star model. So you have to assume that there is in a binary, and from the trajectory that it does on the sky, you get the binary solution of the orbital parameters. Via radial velocities, you get the radial velocities, you fit with a Keplerian law, and you get again the parameters of the system. The other way to find the black holes is if they are unbound. This is via microlensing. In this respect, the astrometric binaries are the most efficient way to find black holes, because astrometry in Gaia can go quite faint, especially with respect to radial velocities, which are really limited to brighter stars. With DR3, 2 black holes dormant black holes were discovered in binary, Gaia BH1 and Gaia BH2. Both are black holes around 9 solar masses. they have a companion that is a star that is around the one solar mass. Both this discovery were quite, let's say, unexpected. What is puzzling is that while you have an extreme mass ratio, especially if you consider the fact that the progenitor of the black hole was even bigger than black hole now. So the mass ratio is much smaller than 0.1, and that you have the companion star of one solar masses that orbits around black hole with an orbit of a few astronomical units. People started to discuss about how this black hole star binary were generated. The main, let's say, evolutionary scheme that is adopted for this binary system is where you have unisolated binaries, the simplest way. So the progenitor of the black hole was in binary with the companion that the black hole has now, and they had an evolution that is they evolved together. The problem of this scheme for BH1 and BH2 is that at the end of its life is becoming a red giant, and then it can easily fill the Roche lobe and start to transfer some matter to the small mass companion. You have even a common envelope phase. The problem with this common envelope phase is that when you have to disperse the envelope, you take energy from the orbital energy of the companion. So the companion starts to do a spiral and go near and near to the black hole, and you expect that you get a merge, because if you have a low mass, you don't have enough energy to disperse this common envelope. So this is something that some claim that you need an efficiency in the envelope removal that is unrealistically high to explain Gaia BH1 and Gaia BH2. So people started to give alternative formation scenarios. One that was started by many people was the dynamical interaction cluster. So essentially you have that this binary is not an original binary, but there was some kind of exchange, and this solved immediately the problem of an extreme mass ratio. And if you have that the black holes acquire the companion after having became a black hole, you avoid the problem of the common envelope phase. There are other scenarios, like if you assume that this is it was a triple star, or you enhance the overshooting in the last phase of the evolution of the black hole progenitor, you can have a smaller massive star when it evolves. And then I cited again the isolated binary evolution, because indeed, if you look at the details of the common envelope phase, this is quite tricky phase, and after you can also have systems like BH1 and Gaia BH1 and Gaia BH2 produced via isolated binary evolution. And this is for Gaia BH1 and BH2. And then it came BH3. So while people were arguing about which is the best scenario about BH1 and BH2, we are with buoyant looking at the preliminary results of our pipeline for the DR4. And when we look at the data, we saw several binary systems with a black hole and either a main sequence star or a giant subgiant. And one of them was really promising, showing an extreme mass function. When we look at the astrometric orbit, it was clean and in agreement with the IBS data. We went to the telescope and got a few radial velocities, and which confirmed our finding. And yeah, of course, we get very excited when we saw that this was the most massive black holes of stellar origin in our galaxy. But then we started quite a long process to ask for ESA for exceptional permission to publish this source before DR4. Why we are spending time in looking at the data? There is a problem with for sure for astrometric orbits due to partially resolved sources. Here there is an illustration of a binary or an optical double star, which is very with a very small separation, which Gaia is not able to separate the two components clearly, and this produces some spurious signal in the astrometry and in the radial velocities that depends on this signal depends on how Gaia is scanning the sky when observing this source. When you do you look for binary systems, you get all binary solutions. You plot them. You plot an histogram as function of the period. You start to see all these peaks, which are clearly fake, and they are due to these scalar signals that generate fake solutions at specific periods that are harmonics of the Gaia precession or the 1 year precession. So you need to filter out all these sources, which is quite a complex job. Well, Gaia BH3 is clearly not a fake solution. You can see here an animation that shows the data as function of time, the motion of the star in the sky, and the black dots are the measurements. Here, this is the orbit. You can see that the measurements cover 2/3 of the orbit. And here we can see the spectroscopy, so the radial velocity is as function of time compared again with the orbital solution. BH3, the system has a period of around 11.6 years. They're quite high eccentricity, and a semi-major axis of 16 astronomical units. It is nearby. It is less than 600 parsec away, and that has a mass function from the astrometric solution of 31 masses. So we already, without knowing the mass of the companion, we already know that this is an exceptional black hole. If we compare BH3 system with BH1 and BH2, here the three systems are plotted on the sky in the same place, let's say. And you can see that the orbit of BH1 and BH2 are much smaller than BH3. So the signal in the astronomy is huge. And you can wonder why we didn't spotted the BH3 in DR3. And it is because the orbital period is so long that in the DR3 time range, we have just this part of the orbit without the periastron, and you cannot constrain the full orbit. So we didn't have we have just an acceleration that was not significant. Here there is a comparison, physical comparison of the orbits, all on the same scale, on the same plane, and compared with the solar system. So you can see that the star that orbits our BH3 black hole as an orbit goes up to Neptune, and while BH2 and BH1 are much smaller orbits. Of course, we cannot see the black hole. So we look at the companion, and the companion are revealed to be an old metal-poor halo star that is now climbing in the red giant branch. The parameters of the star were derived from the colors, sky colors, the magnitude, and the extinction of the unique relative procedure. I will not go into detail, they are in the paper. But here you can see the parameters. So it's a star that is a bit colder than our sun. Is 10 times brighter than our sun, and has a radius that is 5 times the one of our sun. Here we can see the comparison between the modeled SED compared with the Gaia spectrum that is in the red here. We see an excellent agreement. When you compare the magnitude and the absolute magnitude and color of the star to isochrones, you can see that it is the red giant branch. It is a bit colder than expected. We don't have yet an explanation of this, but then we used this plot to derive the mass of the star that is 0.7 solar masses, and then using this we can compute the mass of the black hole, that is 52.7 solar masses. We were quite lucky that the Gaia BH3 star was observed with UVES at the BLT in 2021 in a completely unrelated program. So we used this public spectrum to derive the metallicity and the abundances. So here at the top you can see the magnesium triplet region. People that are expert in spectroscopy, looking at this figure, can understand immediately that this is very poor star, because the line are very, very thin. And indeed, it is minus 2.5 metallicity. Half announced as expected. When you look at the calcium lines in the UV, you see there is no activity of the star, which is completely expected for all the stars in the H alpha and H beta. Something more interesting is that we don't see any enrichment from an evolving companion in the composition of the abundances of the star. There is no trace of carbon-13. The baryon over iron is nearly solar. The rhopium is slightly enhanced, but is normal for this kind of star. So there is no sign of enrichment of the evolving companion, but we must remember that this is now an evolving star, so it has a deep convective. The external part of the star is convective. So if it was enriched, everything was now is mixed, and you will not see any enhancement, any peculiar abundance. Let's go for a comparison of BH3 to the other known black holes in our galaxy. Here in black we have the mass versus the orbital period of a black hole that are known from X-ray binaries. There are these four black holes from spectroscopic binaries, and then Gaia BH2, BH1, and then BH3, which is far more massive than anything else, and with a very large orbital period. So yeah, now we can claim the Guinness record for the black holes, but what is important is indeed the link between this black hole and the gravitational waves. As many of you know, the gravitational waves in interferometer show high mass black holes very frequently in external galaxies. Here is the first black hole merger that involved a black hole of 36 solar masses with a 29 solar masses black hole. And we see these black holes only in these external galaxies and in gravitational waves, and not in our galaxy. So people thought very hard these black holes. So BH3 is the first one of this population. And interesting enough, it is has the same mass of this peak. I don't want to speculate what does mean. I will let this to theorists. What does this say? So we know that from stellar evolution models that massive stars lose a lot of mass during their final phase of the evolution. And if you have a solar metallicity star, these winds are so powerful that you are not able to create a black hole that is more massive than 20 solar masses. This was actually thought also for all the other metallicities. But then in 208, Bing et al. Came with a new recipe for winds, which show that if you have a low metallicity star, the wind is much less effective in taking out the mass. They are much weaker winds. And so both in Padova and here, it was recognized that this means that you can create high mass black holes from low metallicity stars. It was studied with the impact on gravitational wave detection. While in Padova it was more a research in another field. And well, the discovery of BH3, which has a companion that is a very metal poor star, is the first observational evidence that this theoretical scenario was correct. So it is an observational evidence that the high mass black holes that we see with LIGO, Virgo are indeed generated by low metallicity stars. Then another question that we can ask ourselves is how exotic is Gaia BH3? There is a paper that came out in a magazine of astronomy for the great public, the public that said, well, this kind of black holes were expected. So why all this fuss about why this noise is about this black hole? It is expected. Well, if you look at the models, it is not expected at all. For example, there is a paper, Lucas, you wrote it. When you compute, you try to compute how many black holes Gaia should discover. If you look at the black hole of 30 solar masses, you expect 10 to the minus 12 black holes. So it should be impossible to find this black hole. If we put models aside, you can also think about the fact that the companion is a very metal poor star, and the very metal poor stars are rare, very rare. So Gaia should, if very metal poor stars has black holes in the same proportion of normal stars, you should expect to have Gaia BH3 only once every 10,000 or 1,000, 10,000 black holes discovered by Gaia. And while we are just black hole 3, we didn't discover 10,000 black holes with Gaia. So this means that either we were really, really lucky, or most probably very metal pure stars produce this kind of binaries in a much more efficient way than solar metallicity stars. Why? This is an open question. Is this due to the massive solar metallicity stars evolution, because they lose a lot of mass, so the binary system can be the binary bound can be lost, or is this due to the common envelope phase that in solar metallicity stars is destructive, so this binary merges, or is this due to the IMF in low metallicity? We know that people that are looking with James Webb Space Telescope, some of them says that the IMF is more top heavy at low metallicities. So I don't know. Another interesting characteristics of Gaia BH3 system is that its orbit in the galaxy. Here there is an animation of how Gaia BH3 orbits in our galaxy. In red is the sun, and in blue is Gaia BH3 system. And you can see that the system is orbiting in the opposite way. So it has a retrograde orbit in the galaxy, an orbit that is quite eccentric, inclinated, which is typical of halo stars. Well, it is low metallicity stars, and they are quite frequently retrograde and halo stars. But even the BH3 is even more special because it belongs to a stream. This stream is AD2 stream, which was discovered in 23. We can see here the position of, in blue, the position of the stars of this stream, with this red cross being the Gaia BH3. And in the other diagram, we can see the kinematic properties of the ED2 compared with BH3. Again, this system is really in the middle of this stream. So this stream is composed by very metal poor stars with exactly the same metallicity of Gaia BH3. We can see here the color magnitude of this stream, with the blue dots being the members of the stream, and you can see that Gaia BH3 is in perfect agreement with this with the sequence. This stream is thought to be originated from a cluster of a bit less than 10 to the 5 solar masses that was accreted and disrupted by the Milky Way. One thing that is interesting is that given that this stream has a low velocity dispersion, means that when the black hole formed, it didn't got a strong kick it should be a very extremely low velocity kick. Otherwise, the system would not be anymore in this stream. And then the fact that the system is belongs to a cluster suggests that the system was probably formed via dynamical interaction, not via isolated evolution. But we don't really have proof of this. There are two papers already on if Gaia BH3 can be reproduced with an isolated binary evolution scenario, one from Ebad and the other from Yoro et al. The fact that the kick velocity is small means that the orbit that we see today is not much different from what was the orbit before the birth of the black hole. This means that the progenitor, in order to avoid the common envelope phase where the companion would have been merged with the black hole or put in a very small orbit, means that the progenitor had a radius that was smaller than 800 solar radius. Barry found that the black hole progenitor must have expanded to more than 1,000 solar radius, so the isolated binary scenario is unlikely. Yo-Yo and collaborators with the same mass for the progenitor found that the progenitor expanded to 200 solar masses. So the isolated binary scenario is still possible. So this showed that the models for massive stars, especially for low metallicity, still have a lot of uncertainties, and much still is needed to constrain really these models. A last point that I want to do on Gaia BH3 is, can we see the black hole? Well, the companion is a star that is evolving on the giant branch, so it has some stellar wind, and part of this stellar winds must fall into the black hole, and you can compute the light that this mass exchange should produce. We expect something like 10 to the minus 13 solar masses. So this is a very, very small quantity of matter that falls on the black hole. This idea pushed people to look at the system both in X-ray with the Chandra, also in the radio with the array, and we also try to observe it with the gravity, because the black hole, the system is near enough and is large enough that you can, with the VLT and gravity, you are able to resolve this system if the black hole emits enough light. And well, everybody failed to see the emission from the black hole. Capelluti et al. And collaborators got upper limit for the mass of the accretion on the black hole, that is 10 to the minus 12. So it's still not really reaching the current expected rate. But we are now at the apoastron, and in a few years it will become the star will arrive to the periapsis, and it should be much brighter than now. Of course, in 29, I don't know if Chandra will be still alive, or if there will be any other X-ray mission that will be there to observe this object. Okay, let me close this talk with some perspective for DR4. Everybody is waiting for this DR4. I can say, I hope I will not break any secret from the Gaia DPAC, saying that the binary processing that was implemented that is now being implemented in DR4 is much better than what was done in DR3. In DR3, there was really a strong and conservative filtering of solutions. So many real binaries were thrown away. Now we are filtering much better the partially resolved the sources, which are the problems. And we should to get a few million of binaries. So at least 10 times more than what we have with the DR3. And even we expect a few million of astrometric acceleration, which are binaries with periods larger than 10 years. How many of these will be black holes? This is a plot of from El Quadri, where you can see the various predictions published in various papers, which unfortunately go down, 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 and then the DR3 with just 2 black holes, or well, we can see 3. So we hope to go back up in DR4. Yeah, so we hope to go to 100 black holes, but I cannot promise anything. But for sure, we can start constrain the black hole population and really give more hints on massive stars and binary evolution. There is not just binaries, but also microlensing. So as you know, more than 300 microlensing events were published in DR3. And this resulted in 4 black hole candidates. And another candidate was black hole candidates was found again here from Science Alert. One point that must be thought is that DR3 microlensing were events were parameterized only based on photometry. And it is difficult to constrain masses if you have just photometry. But therefore, we'll use also or the microlensing from DR4, we use also the astrometry. So we will have many more of this interesting microlensing event where you see the effect of a lens on the astrometry. And also the epoch astrometry will be released with the DR4, so everybody will be free to look at the astrometry and do their fitting. So conclusion, this amazing mission that is Gaia permitted to discover this exceptional stellar black hole, Gaia BH3, which is the most massive stellar black hole so far discovered in our galaxy. It is the second nearest stellar black hole, so there must be others of this giant around in our galaxy, waiting for to be discovered. It is the first black hole from a very metal-poor star, and this makes the first observational evidence that high-mass black holes detected by LIGO Virgo gravitational-wave interferometer are generated by low metallicity stars. And also the fact that is interesting by the fact that it belongs to this globular cluster, retrograde globular cluster that was disrupted by our galaxy. For sure, BH3 will be studied extensively for the implication on gravitational wave, events origin, on the massive star evolution, especially at the low metallicity, the evolution of a binary system. It is also bright and nearby, so it can be easily studied from ground. So it is indeed a unique system also to do other kind of studies, like study of the accretion physics on low rates. There is people like Colaviti et al., which even suggest that if the dark matter is some kind of action field, this black hole should produce a signal in the gravitational wave. So it's a laboratory for exotic physical phenomena. And well, I conclude with, well, I don't know how many, but more black holes and other surprises are expected in DR4. Thank you for your attention. Thank you.
I'm looking at the video you're showing. Do we have any questions or comments? Przemek?
I have a question on DR4. Do you, as Gaia Collaboration, plan to publish one of these validation papers with the black hole catalog, or
yes,
or will you just put out the astrometric solutions and let the crowd dig into the data?
We are planning to do, can I say this? Well, we are planning to do a black hole paper, yeah, with candidates, yes. Of course, we are not going to study in details, but it is really for validation to see if these candidates are good or not, and show how to see if how you can trust to the solutions. Indeed, the point, the problem with the DR4, the DR3 was, for example, that 1/3 of, no, more than 2/3 of the high mass function solution were fake solutions. And I think that our duty as a Gaia community, as a consortium, is to try to give as much clean data as possible and try to give a clean sample to the people. Of course, people will be then free to look at things that are more difficult to find and go into the noise and enjoy.
Any more questions? Comments?
It's striking that the companions are low mass. I assume this is because they are very ancient. So the more massive companions must have evolved by now. So do you expect a number of white dwarf black hole binaries or neutron star black hole binaries?
Well, neutron star and black hole, we will not be able to detect as binaries with Gaia. Well, it is possible that via microlensing you could see them, because I mean, if it is a neutron star, it almost doesn't emit light, so you don't see, but it will maybe show up as an astrometric signal being in front of for background stars. For white dwarf, yeah, this is interesting. Actually, we have binaries where the main star is a white dwarf. So typically a brown dwarf orbiting around a white dwarf. We didn't yet saw any black hole around or any white dwarf around the black hole. Maybe.
One? On Zoom? So let me ask maybe the last question. I was wondering if the finding of BH1, BH2, and BH3 changed your way of looking at the data that's going to be published in DR4, in the sense that, okay, we're going to have more data, they're going to be like more precise as you showed, but have you changed some of the like either limits or like some assumptions that you were using in DR3 that is based on learning of what we found so far?
Well, let's say that for DR3, the processing of the binaries, it was the first time that we produced binaries. Okay, so we didn't have experience. That's why all these fake solutions were not understood, were not well filtered out. Now we gained a lot of experience from this, not especially from these 3 black holes, but for sure the fact that these sources were published and discovered outside was a stimulus for us to improve our processing. And this experience, well, you will see in DR4.
Thank you very much. Thank you, Pasquale. So thanks a lot.
Thank you.
So for those of you who don't know, the video that Pasquale is showing has also music that was actually kind of prepared by Łukasz Wyrzykowski, so you can also search for it online and enjoy it. And next week we meet William Person from NCBJ. We'll have a talk about galaxy mergers, I think. And for students, if you didn't put your name in this notepad, please notebook, please do so. Thank you very much. Thank you.